Yeah?
We'll start here.
Yeah.
I've tried to find Andy, can't find him.
That's all right. Okay, so my name's Sarah. I'm going to talk to you a bit about what we do at the lab that I work in down in Oxfordshire, where we've made our own stars on Earth. So first I'm going to tell you a little bit about why we're doing this. So this is a satellite image of the Earth taken at night. You can see all the lit up places of all the cities in the developed countries. Now if we have a look at how we think this is going to be in 2050, we think that with the population going up and with developing countries being brought up to the level that we are at, we're going to use a lot more energy, and so that's why you're getting all these much brighter dots and more light showing up in the countries at the moment that are developing countries. So this means for us that we're going to need a lot more energy. So with the world population increasing as we think it's going to in the next 50 plus years, even with a moderate model for how we think the energy consumption is going to go up, we're still going to need to get a lot more energy from somewhere. So at the moment, we're using fossil fuels. Now that's been fine, but they take millions of years to form, and we're using them far too quickly for there to be enough left for us. But on top of that, the CO2 emission that comes from the result of using those fossil fuels is contributing to the global warming problem. So what we need is something clean and something that isn't going to run out. And this is where we think the energy from fusion, which happens in the middle of stars and the sun, is the way to solve this problem. So that is what we are trying to do. So just talk you through what fusion energy is. So this is when we have two light nuclei that fuse together, and then they produce a larger nucleus and a neutron. Now the larger nucleus is actually not as heavy, there's less mass there than the two original nuclei that fuse together. And it's this change in mass which we can convert into energy using Einstein's famous formula equals mc squared. And it's this energy that comes from the change in mass that we're trying to harness. So how do we do it? We know that the sun, spinning around there, and stars, they're all really, really hot, as Jenna's just been saying earlier. And so we need to get this to tens of millions of degrees C to get fusion to happen. But at this temperature, we can enter a different state of matter, which is a plasma, and you may not all be familiar with this, so I'll just run through the things that hopefully you are familiar with, starting with a solid state, and then I'll explain the difference between all of these and a plasma. So in a solid state, you've got all your atoms with your electrons spinning around the nucleus in a nice regular state. Now if we go to a hotter temperature, taking water for example, and melt the ice that you have in the solid state of water into liquid, you've still got your atoms, but they're moving around a bit more, and now you've got your flowing liquid. Now, if we heat that up even more, for example, boiling your kettle, getting steam, we get a gas. So again, atoms, but they're moving around a lot more, and they'll fill all the space you've got. Now, if we get even hotter to a plasma, you no longer have just an atom. All your electrons have come off the nucleuses, and instead we've got negatively charged electrons and positively charged ions that are basically making a big super particles that are going to expand everywhere. And this is what we have, and this is what we need to make. Now, because these are charged particles, we are going to have a bit of trouble bringing them together, because just like a magnet, if you've got the same charges, and it's the positive bit of the bits of the plasma that we want to stick together, those nucleuses, like I said before, that release the energy, we need to overcome this thing that's keeping them apart and trying to repel them. So if we just try and put them together, they'll do this, and they won't want to fuse. So we need to get them beyond this barrier that they're causing. If they get close enough, they will fuse. So we need to heat them up so they're going really fast, then they're going to collide, and then we'll actually get fusion. So that's what we need to do. So we've got to get these nice and hot. But as I said as well, they're charged particles, like the gas, they're going to go everywhere, and we need to find a way to bottle this. Now the sun works because it's so big that the gravity pulls it together and holds it together. Obviously we can't make a sun the size of our sun or a star on Earth because it will be bigger than us. So what we use is magnetic fields. So because they're charged particles, they're going to follow a directed field line. So if we apply a magnetic field in a direction, for example, like along this tube, then the ions and the electrons are going to oscillate around these, and they're going to follow them. And so this is how we're going to try and contain how we have them. Now obviously if we just have a tube, it's still going to run out the other ends. So the design we use when we're building our stars is a tokamak. Now basically what we do is we take that tube, we bend it round, and then you've got a torus, or as I like to call it, the donut design, because that makes it a lot easier to understand what we're talking about. And basically it's this design that we use for all the stars that we make on Earth, because it's the best way that we can use to contain it. Now I will show you, this is going to be a video of the machine that we've got in the UK that I work on. Now before I start it, just to put it into context, this video is going to go on for almost 2 minutes, but we actually only have our plasma for a very short time. So we have a pulse device and it lasts like half a second. So this is really slowed down, and we use cameras that slow it down so that we can actually see what's going on. Because in that time, because everything's so tiny, there's loads of stuff going on. So I'll play this now. There we go. And from my point of view, this is quite a small machine. So when we get into the stage where we want to try and put this as a power plant to the grid, we're going to need to go a lot bigger. But it's still 4 meters tall, which is quite a lot bigger than me. So we start by injecting a gas. So this bright spot here is where the gas is coming in. And also notice that this shape is a bit of a different to a donut. It's a bit of a more of a chord apple. That's a different, just a slightly different design that we use on our machine. So what we do is we fill it with gas, we ionize that gas to a plasma, and then we use our magnetic fields to hold it. So you can see the bright bits is where that plasma is interacting with the side, and every now and again those bright flashes, they're basically our equivalent of a solar flare. So when the plasma gets really hot, it tries to throw out some material just like a solar flare does. I'll come back to these later because they can be a bit of a problem. But basically what we do is we use the magnetic field to try and hold it, but then we have to use a second one to try and direct it so that our heat can come down to a section of the machine. So it's just like a tin can that's holding this, and it's the magnetics that are holding the shape of it. But there is one part where we have an actual material surface where the plasma will come into contact, and so we do a lot of work on designing that so that it can handle this heat, and that is where I mostly do my work. So what we use is magnetic fields to direct this very thin bit here that's brighter, and it's actually brighter because it's colder, just because of the way it emits. So you'll see straight through here, just because it's so hot we can't see it with visible imaging, a bit like all the stars and galaxies that Jen was talking about. And here the bright bits you're seeing is where it's actually touching these material surfaces. And because we've got these center bits that are really, really hot, and this material can't handle this, a big problem for us is working out how to get that temperature to reduce before it gets to those materials. So this is one of our biggest problems, that we need these great temperatures of more than 10 million degrees C in the center so that the particles are hot enough that they'll actually fuse together. But because no one's made any super good materials, well, I shouldn't put material scientists down. They've made some really good materials, but they're not genius. Well, they're geniuses, they're not superheroes. So they're not the kind of materials that can take the source of heat that we're going to have going down on here. So what we have to do is try and keep this bit really hot and then try and cool the edge bit down so that it doesn't destroy the materials we have to put in to physically hold this star together. So our biggest challenge is keeping it really hot in the middle, but not too hot at the outside, and it's only going to get worse. So our machine's like 4 meters high, and as I said, for us it's small because it's an experimental reactor. But when we want to make power stations and bigger machines, there's one that is an international collaboration that they're building. That's going to be 20 meters high and a lot more powerful. So the problem is only going to get worse, because the hotter the middle gets, the hotter the plasma that's going to touch surfaces are. So we need to try and find a way to reduce this heat. Now I've got some, just to put this in context, this is where we're at with our machine now. So the kind of heat that comes out of your kettle, not too much of a problem, we can handle that every day. Car engine, a bit hot, obviously we have to have quite good cooling systems to keep your car running, and that's kind of where we're sitting now. This is a sort of limit to the sort of materials we can put in these machines that can handle it. We're going this way, the bigger our machines get, the worse it's going to get. And this is exactly what we don't want to happen. So when you're welding, as you can see, there's all the materials sparking off because it's so hot, it's melting and it's spewing. We don't want this happening in our machines because it's just going to make our plasma diluted and it's going to stop the fusion happening. So however hot we have it, if all of this is getting in, it's a complete waste. So we've got a few ideas, and this is the sort of research that I do on how to reduce this heat that reaches these material surfaces. So one is to try and spread it over a larger area, just like with pressure. If we've got the same heat but we can spread it further, it's not going to do the same damage to the area that it's touching. Just like if you put an elephant in heels, it's going to make more damage than if you put him in his normal feet. So that's one way of doing it, to try and spread it. Another idea is to try and cool it. So as it comes down these channels that we've designed with our magnetic fields, we can find a way to try and cool it down without it cooling down the center of the plasma. And then the other thing we've got to worry about is these little solar flares that you can see in the video. They can be quite damaging, so that's another issue we need to worry about. So first, this seems quite simple. If we've got the same channel of heat coming down, and that doesn't change in width, but we just make our radius bigger because it's a round donut, we can just increase the area, and then we've got it over a bigger area. It's going to help the problem. You think, that seems so simple, why don't we just do that? I wish it was that simple. Unfortunately, in order to direct that heat, we need the magnetic fields. So you can either make the whole machine bigger, but then your heat goes up anyway. Or if you just want to make this bit bigger but keep the same size plasma, you're spending a lot of money on the magnetic fields to direct all that heat, and that's just going to make our electricity too expensive when we get to a power station. So it's a good idea, but it's not going to work on its own. It is something we're doing. So our machine that I showed you a video of, we are currently upgrading it with some of these new ideas to test them. And we are going to use this in ours, but it's not the only thing that's going to do it. So another idea is to try and extend this leg and try and cool the plasma as it goes on its journey before it touches the material. So if we extend it, just like if you stick something that conducts heat into a hot, say you put something in a fire and then you put the other end in an ice bucket, you're going to get a change in temperature. And even though it's really hot one end, it's going to cool before it gets to the other end. So if we make this longer, even though it's quite hot here, by the time it reaches the surface, if we extend it, you're going to get it cooler. Again, you've got the issue that if you make this really big, you're paying for magnetic fields that you don't really want to be paying for. So we can do it two ways. If we put some gas in there, if you remember our plasma is all charged, that's why it's following the magnetic fields. Or if we put a neutral gas in there, it isn't. But if we put enough in here, it's going to exchange some of the heat through collisions and bumping into the power that's being streamed down this channel. But because they're not charged, they're going to take the heat away, and it's not going to impact on the same small area. Now we've got to be careful, because obviously if these colder particles get up here, they're going to cause just the same problems than if bits were coming off our material surface anyway. So you also need to enclose this so that this bit stays nice and cold, but it doesn't affect this bit. And again, this is something that we're doing in our new machine. So this is the setup that we originally had, and we're going to take this to a longer distance, to a larger radius so the area is bigger, and then we're going to close it off so that we can fill it with more of this gas and cool it down. And we're hoping that's going to make a real difference that we'll be able to use in future power stations. Now, problem's not solved though. This is still quite a big problem. So if you look at the sun, these are your solar flares, and this is basically what these big bursts that we were seeing on the video can do. So that as you can see, these, just like in the sun, they're spewing out energy, particles, heat, and this is what's coming out here. So whereas before we had that nice smooth edge, sticking out from here are all these bits, and you see they're lighting this up a huge amount, and all of that is extra heat. So this is another thing that we're still working on, and there's a lot of work to be done to try and either stop these from occurring altogether, or at least make them a lot smaller so they don't cause as much problems. Because at the moment they can be up to 5 times more damaging than the constant stream of heat that we will get. So if any of you feel like being future fusion scientists, this may be something that you can help us with. But basically, the aim of all of this work is to get to the stage where we can get fusion power to the grid. So what we'll do is once we've got our nice efficient plasma and we've solved all these problems in containing it, we'll then be able to use it in the same way that when we burn fossil fuels, we heat water, drive a steam generator and turbine, and get electricity to the grid. So this is what we're aiming for. And I promise you we will get there. It's just taking quite a lot of work, and we need all the future minds to help us work on fusion so that we can get this, because it's definitely a need for future generations. So I hope you found this interesting and it's inspired some of you. But if you want to find out any more, please look at our website. We've also got Facebook and Twitter. And also, if you're really interested, we do have open days at the site, and you can come and have a look around the machines. And also school tours can come. So please let me know if you are interested in finding out about that. Thank you very much.
Thank you, Sarah.
So is that the machine itself?
So this is what we're going to have in our... so the video I showed you is this machine, but this is the upgrade we're having.
Right.
So this is an artist impression of what we're going to end up with. So before it's sort of finished there, And now we've got this new section here, which is where we're going to put all the gas in, try and cool it down, and then close it off there so it doesn't damage the upper bit. And this is literally being built as we speak. It's in pieces in our big lab. So I think it's all in except the lid. But yeah, so.
Is this the same technology they're looking at with the Hadron Collider?
No, it's not. A lot of people think it is because you spin that round the same sort of way. But these, like the Hadron Colliders, are a much larger donut, if you see what I mean. Whereas these, our particular machine is like 4 meters high and 4 meters diameter, and these are purely for trying to get an energy source for the future. So as much as there's fundamental physics that's interested in this, it's purely the main aim of all the research we're doing is to try and get this to the grid eventually.
So that's basically going around a lot slower.
No, I think the particles are going just as fast. It's just they're not controlled in a very small route for collisions, if you see what I mean. Yeah. So in the Hadron Collider, I don't know a lot about it, but that you're trying to bash particles together, whereas we've got basically like a super plasma that's got all sorts of stuff going on. But it's a lot more going on in there than I can possibly get into in a talk like this. So as much, it looks quite calm in the middle, but it's really not. If you can look at a lot of the things that Jen was talking about with microwaves and all these other kind of radiations, when you look at that, you can see there's an awful lot going on with all the particles moving about. So that's why it's not quite as simple as just making a sun and it working.
This international collaboration you mentioned, they're actually building this in France, I believe.
Yeah, they are. So I actually went on about 4 years ago now, maybe. 3 years ago, something like that, I went and did a bit of work there. So they're doing quite a lot of work on it, but it's taken a long time to build, partly because it's an international collaboration. They're getting coils from different countries and it's all having to get shipped to France. So it's a big piece of work because, as I say, like our machine is 4 meters tall, that's 20. And because of where it is, they've had to like dig a massive pit and have like earthquake towers to stop it being any problems. But it's getting there, and that's the sort of thing, like anyone that's wanting to do this now, they're calling them the ETA generation because they're going to be working on that machine, and that machine's going to make huge strides in fusion energy because they can do so much more with that than we can on our own.
Estimate when this thing will finish?
I think mid-2020s is when they're thinking it will start up, but it's all a bit up in the air. These projects, unfortunately, because they're such big projects, it's very hard to put a date on when it'll exactly be finished, but it will definitely be worth it when it is.
Safer than nuclear energy?
It is nuclear energy, but it's like in essence it is completely safe compared to fission. So it's the opposite reaction. So with fission, what you have is when you start the reactions, it's like an avalanche and they just keep splitting, and that's where you get your energy from. Well, we're trying to do the opposite thing, so it's a lot harder to get it going, but it'll only go to a point. So we'll never get this in the kind of fuels we put in ourselves. But in the sun, what you do is it fusions from hydrogen all the way up to iron, and then that's when it's easier to then start splitting them. So the thing with these is, unlike with a fission reactor where you have to put in like moderators to try and slow down the energy production, with ours, because there's so little amount of fuel in there, and because of the way we have to hold it with the magnetic fields, you turn one thing off and it'll go off. So there's no risk of it coming out it's inherently a safe thing because it's so easy to shut down. Yeah, that will never happen with fusion, so you're good.
Is there any sort of waste? There's no waste?
So to go with a proper fusion reactor to be as efficient as possible, what we use is, at the moment, all our reactors use heavy hydrogen, which is deuterium. The easiest cross-section to get it to fuse is actually deuterium and tritium. Now, tritium is radioactive, so there will be some amount of waste, but it's nowhere near like the lead times. It's not got the same dangerous half-lives as all the stuff in fission. And they are already now, at the site that I work at, working on ways to handle that so that we know exactly how to deal with it by the time we get to that stage. But for all our experiments, it's not worth using it because it's the same physics. It's just that if you use tritium, it's a lot more efficient when you actually get the reactions. But the good thing with this is it is so much cleaner and safer than fission. But there is an abundance of material to use to make it happen. So that's why it'll be so much easier than anything like fossil fuels.
I'm surprised that with all this technology, you still end up with a steam and almost a steam engine.
It's because the bit that we're making is just a new way to heat stuff up, because that's the bit we're running out of. I think the other bit, if you look at power plant technology, they've done so much to make that as efficient as it can be that it's still the best way to do it. So all we need to do is make essentially the fire bit that makes the heat just easier, more reliable and safer.
That's what it is, just a fire.
Essentially, yeah, we're just finding a different way to burn a fire, but it's a lot more complicated than just starting a fire, unfortunately.
Cool, thank you very much.
Thank you.
Jen's back next with
Oh.
the